Who you are?
I'm a student of Engineering 11 class. My name is Shani Bek, and we're doing the SLI project for the Foothill College, which is helping you guys to solve the problems lot 4. You know, when you came around at 10 or 11, the parking lot is full, and you don't know if it's full or not.
So that parking lot up there,
Yeah.
the one on top, you know when you're driving around and you always ask yourself the question, is there a spot, is there not a spot? Okay, so the college has the following question. So what happens when you drive up there, there's no spot? What do you have to do? You got to go back on all the way around. It wastes your time, it makes you late for class, and it wastes gas, right? Okay, so the college has the following question. Is there a way, continuous problem, actually, it's actually kind of discrete too, but yeah, there's image processing stuff. Is there a way to be able to have an automated process of figuring out whether or not there is an open spot? Okay, so what he's about to describe is that. What I might do, if it's okay with you, Jean, is show the screen here. So first thing I do is, can you just push play and kind of discuss what we're looking at right now?
So we're looking now at we have a camera that recognizes the cars and counts if car is going in or out, and also helps faculty staff also to see if they have a parking spot there also.
Could you just keep playing it?
Yeah, and here the a demonstration of that.
Do you see the count?
Yeah.
What do you think? Do you think you need what type of data type would you use there? Double? There's 2 of the 53 cars in there.
Yeah. So this car is coming from faculty, and it counts as -3.
Yeah, I was telling John that. Okay, I have tens of things that I can say about this in terms of numerical analysis, right? Are they paying you for this?
Yeah. They pay.
You're making money on this project.
Mm-hmm.
If you have questions about this exact project, you can ask him. Do you know what software you're using to do this?
OpenCV, Python.
Awesome.
And it's so our project has 2 ways of solving this problem. One through sensors and one through camera, computer vision. And for sensors, we're using the hexadecimal commands to send the commands if car is in or out. And then
that made me laugh. So he came to me one day and he's like, "Hey Jeff, I'm using hexadecimal in an actual thing, so your class isn't useless." You didn't say that, but I said that.
So, yeah, and we're going to continue it next year also on this project, but I won't be here. But I think other people in my project is going to continue this work also. So we'll probably next year it will deliver final product and it will be there already.
What club is that?
It's not club. It's Foothills Inside Project Science Learning Institute.
Oh, okay. So if you're interested in this, you could go to SLI and learn more about it.
Yeah, you can join the project next quarter.
So, when I saw this, I see a ton of other things. Do you remember we were talking about data classes? This is what I would call an image data class. It's actually a movie data class, and each one of these pixels, there's a lot to be said about this. I would imagine that they're using an automated object tracker.
Yes.
Yeah. So that automatic. So here's what I like to think about this. When I was working professionally as a mathematician, getting paid to do research as a mathematician, I was designing numerical analysis algorithms to do specific things, right? So what happens on that is, from the numerical analysis algorithms, they build deep learning software. So deep learning is the leveraging of numerical analysis software at a very, very high scale to make conclusions about a particular set of objects on top of that. And then project teams like this will take those algorithms and apply them to specific problems to make headway on them, right? Now, I'm not claiming everybody that learns numerical analysis has to get to a space that they design their own algorithms from the mathematical first principles, right? But I am claiming that, here's an example. Jean is working on a beautiful project, and he's having to send information from sensors to a receptor, and the way that the receptor decides that is based in hexadecimal. So in order to take advantage of that particular idea, he has to have some familiarity with the numerical analysis concepts. In that case, it's a hexadecimal representation, right? In order to do that.
And also gives a lot of confidence when you see these numbers. Like, so a lot of guys did in this project, they didn't take a engineering 11, and they didn't know about the binary representation of numbers, and they were like very confused when they opened the manual and instruction of how to send the data to the server. And when you know kind of science behind these numbers, it gives you a lot of confidence, and it doesn't create anxiety that you don't know nothing about these kind of numbers.
So you're telling me that the stuff that you learned in this class, you immediately leveraged in a technical engineering space where other students had taken a bunch of computer programming classes,
yeah, but
they didn't have access to the information, and you could teach them based on this material.
Yeah, and they were more confident now.
It's almost like I planned that. Seriously. I did plan that. Because I recognize this is a fundamental concept in this space, and if you have this, you're going to have an unfair advantage when you go on to future classes. You will have access to information that is not taught well at the introductory level, but is expected if you expect to do anything useful in the world. So let's give him a big round of applause. Claim, if Jean can do it, you can do it. If I can do it, all of you can do it better because you're just cooler people, right? And smarter and better dressed.
Select so from OpenCV, we didn't write the object detection. We just took somebody's work from OpenCV and we trained this machine learning thing for our needs.
Is it OpenCV?
Yeah, OpenCV.
Okay, so let's go back
It's
here.
called SSD. Yeah.
Okay, so the reason I want to expose you to this is we're about to go very, very deep into it. And it's not always clear why we're doing this, but that's the type of work that this stuff leads to. So what I want to talk about now is the beginning of our first numerical algorithm. And I want to talk a little bit about the math behind it. This gets into a larger theme that we'll talk about next time. So this is going to be the function that we're working with. So we want to create an algorithm to calculate this. And I feel drunk, which is not good because I didn't earn it yet, right? So our input is going to be a number x, and our desired output, what's the desired output that we have?
You should fix the screen so we can see what you're writing. Because it's not showing on the live stream.
Oh, thank you so much. God. When you students go famous, don't forget about us, okay? Remember. Okay, so we had this concept of doing this, right? We start with our continuous variable, we approximate that with a numerical input that's stored on a computer, we create an algorithm to solve the problem, we approximate the output, and then we pray that the output that we have is what we were hoping for. So our desired input is going to be a math variable, and our desired output is going to be also a math variable. Before we do any work on the algorithm development side, I want to do a little bit of pen and paper analysis. So if I set x equal to 2, what does that immediately mean about y? Y would be the square root of 2. Anybody know whether or not this number is a rational number or an irrational number? Irrational. It's actually a type 2 number. So it's non-rational and it goes on forever. Okay, so let's go ahead and look at this. If y is equal to the square root of x, What if I wanted to get rid of the square root? What would I do to get rid of the square root? Square it. Okay, so this would mean y squared was equal to 2. And this also would mean y squared minus 2 is equal to 0. Which would mean we'd have a function, I better be careful. What's how I do this? We'd have some new function where I'm putting in an input and getting 0. So this thing right here, g of y, is going to be the function y squared minus 2. Okay. So now we're going to define what we call a root problem. This is a very, very famous problem in numerical analysis. There are 1,000-page books written on this exact problem. Let me repeat that. There are people that have worked in 40 years careers and produced mountains of research on this thing in this box. This actually serves as a fundamental underpinning of many, many, many numerical analysis problems because it is so popular. So we're going to call this problem find the quote-unquote roots of a function, any function, it doesn't, not just the one that we just talked about, g of y equals 0. And another way to say this is find the y values that produce a 0 output. So if I have some function, in this case, what was our function called? So here's the claim. Do you notice what we just did? We took a square root problem and turned it into a function equals 0 problem, right? So even though you might not think about it, the square root problem leads to a when is a function equals 0 problem. There are many, many situations where you can take a problem that doesn't look like a find a function equals 0 problem and turn it into a function equals 0 problem. I'll show you one of those on a TI calculator in just a bit. So let's do this for this example. Remember that the original problem that we had was to say let x equal 2 and find the square root of x. Okay, and then that led to, after a few minutes of analysis, the following problem, right? So I know, because I'm down with it, I'm down with the Facebook and the Instagram and the Snapchat, that WTF means want to find, right?
Yes.
Thank you. We want to find y such that, actually I'm not down with any of those technologies and I think they should all leave. So, yeah. That's a different conversation. So we want to find the y such that g of y is 0. Let me ask you this. What does that look like? What does y squared minus 2 look like? Can you draw it in the air? And let's do it with the fight the power. Use your middle finger. Yeah, you see it? Where's the vertex? So let's call this 1. We'll call this 2. The vertex is at the point 0, negative 2. And we'll call that 1. We'll call that 2. We'll call that negative 1. We'll call that negative 2. Ah, sugar. Say it again. At least 1. I would bet my life on that. Yeah. Okay. What do you know about the solution to this problem? Where does it happen? Yeah, in fact, the solution to our original problem here is right there on this graph, right? Ay, ay, ay. My 1-year-old is starting to say, ay, ay, ay. It's the most fun thing in my day today so far. I said it this morning. He's like, ay, ay, ay. So if I could find those 2 points, I would actually solve this problem. And if I solve this problem, which point would give me the solution to the original thing that I wanted? Which of those 2 points give me the value of square root of 2? Yeah, okay. Okay, positive square root of 2. If I had positive square root of 2 and I was using IEEE format, what would I do to get the negative? Flip the sign bit, right? So if I get this one, I get the other one for free, right? Okay, so what that means is, let's zoom in, and this would be a really good space to use MATLAB's. If you're looking at this and thinking to yourself, how would I ever think this alone? What I would say is, if I shut you in a room for many, many years of your life and gave you just water, coffee, and maybe a little bit of food, and I said your whole life depends on your ability to solve this problem, I guarantee that you would come up with this, especially if you had access to a textbook. Okay, so claim, if we can solve this problem of identifying exactly where this freaking thing is, right? We know what this graph looks like. This is y squared minus 2. So if I can find this problem where this is, I'm done, right? Okay. So let's talk about a value that we definitely know how to compute. What is that output value at g of 2? So the x value is 2. The y value is g of 2. What's g of 2? 2. Okay. And then I want to say, guess what is true today? Math 1A is not useless today. There's this really, really beautiful thing in Math 1A that says, slapping a base. I'm slapping a base. That if I have a point on a continuous curve, I can slap a line on that curve that touches at exactly one point, and that line is called the tangent line. I could also call it a linearization. Okay, so now I ask you. I don't have a beard and I don't have a pipe, but if I did, I'd have the ability to think for myself, right? What's the equation to the linearization? How do you slap a tangent, the equivalent of a tangent plane, onto a surface? No, it's a tangent line. It's a one-dimensional tangent plane.
Yes.
I did that because I remember having the conversation with her, and she like blew my mind with how deeply she understood this concept. And I was looking at her while I said it, right? So there's 2 things that happen, right? We go through, I guess I should be a little careful here. We go through the point itself, and then we also match the first derivative at that point, right? Okay. So you're telling me that I actually could calculate, and maybe I call this y because we're thinking about the input as y. Do you remember this? That the idea of the tangent line matches the point exactly and also the first derivative of the point? It's also a first order Taylor series approximation. Okay. So let's go ahead and look at this. So L of y is g of a. In this case, what's a? 2. Plus g prime of a outside of y minus 2. So this is 2 plus, well, let me ask you this. if g of y is y squared minus 2, then what is g prime of y? 2y. So this thing now becomes 2 times. So that means g prime of a is 2 times a. But what is a? 2. And then here I've got y minus 2 because that was the 2, right? So now I know that this is 2 plus 4 outside of y minus 2. Well, what did we say we were looking at? So this is now the equation of that line. What were we trying to find? We're trying to find this this beautiful thing, right?
Yeah.
This mother father, no?
Yeah.
Okay. Well, riddle me this. I don't know what that is, but I have an equation for a line. Let me ask you, is this equation vexing or non-vexing? Uh-oh, we're in trouble. Addition or multiplication, subtraction, uses numbers that actually have exact representations in IEEE format, right? Well, I don't know this, but I have an equation for this line. Could you guess how I might approximate? The y value at which the line is 0 may be closer to what we want than the initial y value of 2, right? Okay, so you're telling me that if I had this thing, that would be, I don't know, maybe what I would call my first approximation. But then you're telling me, well, you didn't actually tell me, I'm gonna do something. If I know this y value, I could actually get an approximation for the output at that point. And once I have an approximation for the output at that point, I could do what? Put another tangent line in. I could use my original linear approximation. Once I have that tangent line, whoa, what are you noticing? If I project that tangent line down onto the axis, it's really darn close, and then I could project it back up, draw another tangent line, and eventually, if I do that, what's going to happen? I'm going to have my point. That's called Newton's method. He did this in the 1600s, but you know what Newton didn't have? A computer. He did this by hand. And this is where we would like to go back to his days and bring a computer with him and make him feel real stupid, right?
Yes.
Be like, this is for what you did to me the first time I took calculus. You mother. Father. How do you know when to stop? Let's get to that answer in just a bit. So she just asked the analysis question. We just had what I would call the inkling of a good idea. Thank you, Newton. Okay, so let's go back and think about this for a second. So this is a process that when I was doing this, get paid as a researcher, took about 1.5 years for the fucking idea. And guess what? 97.999% of the idea I stole from other people. That was funny. Okay, not funny at all. Cool, real cool, guys and gals. And why I want to say this is, so I just casually introduced the major idea behind this algorithm. Have you ever been in a class and felt like, how would you ever think about that? This is why you are in school, so you can study a bunch of other ideas that people have, and then if you were going to go to solve a new one, you could steal them at will, right? So before we do this, in order to solve this problem well, what is the major idea to find the zeros of this thing? So if I have a function, so let's go back to the original problem. What's the problem called? I'm doing my life here. Oh, there it is. This is called a Root problem. Okay, what is a root problem? You have a function, and you want to know where is the function output 0. In other words, what are the input values where the output is 0? What's the major idea here? So if I think about what the approach is, think about the graph of the function, take some initial guess. Project that guess onto the graph, and then do what? Define a tangent line at that point. Find where the tangent line is 0. Once I know where the tangent line is 0, take that new approximation, project it onto the graph, define a new tangent line, project that thing down onto it, and if I keep doing this, what is eventually going to happen? Going to get really close. We have a question, well, how close can I get and when should I stop? We don't know the answer to that question yet, right? But if I were to do this, the optimal object that I'm going to be working with is called a line. Okay, so I would ask you immediately, what do you know about something called the point slope form of a line? Okay, so what would that immediately mean if I wanted to get the output on this thing? This is y1 plus m outside of x minus x1. So, in other words, for any linear approximation, I'm going to have the concept that I approximate. I don't like the notation that I used in this particular case. Okay, so let's think about this for a second. So my notes here, I would say I give them a solid D. They exist, but they're not very well done. So I'm going to just diverge from this for a second one. So we're going to call this G of Y, right? And we'll call that point Y G of Y. And then what I'd like to do is I'd like to create a tangent line approximation for that maybe we call L of Y. So careful, these y's are not the same. This is called algebra. Usually we think about the input variable as what? X. In this case, what's the name of the input variable? Y. So you got to be a little careful here. Maybe we have this new thing called like W equals W1 plus M outside of Y minus Y1, where the output variable is W and the input variable is Y. So what I want to do is I want to come up with a general approximation for the tangent line at that point. Well, what did we say the tangent line will always do? What point do we definitely know is on that graph? I'm not talking about the specific, I'm talking about the general. What's the input? Y. What's the output? G of Y. So let's call this our initial guess. Okay? So what's the point on the line? Point is going to be our initial guess and G of the value at our initial guess. Right? So our initial guess, G of the value. What's the slope at that point? Yeah. G prime of the initial guess, right? Okay, so then let's go ahead and define this. We're going to have an output. What's the output value at that point? the output value is this thing, plus what? G prime at that times okay. Now we can go back in and actually think about for our exact value of g, which was y squared minus 2, and for our initial guess. I think we used our initial guess at 2, right? So let me ask you this. Did we just like roll a dice and guess 2? We're trying to get the square root of 2, right? We knew that the square root of 2 was going to be a place that the y squared minus 2 graph touches the curve. We knew that was going to be somewhere between 1 and 2 because 1 squared is 1, 2 squared is 4, so it's got to be somewhere between that, right? So we say to ourselves, like, okay, well, y naught is 2. So what does that mean about g of y naught? Well, it's going to be g of 2, which in this case is going to be 2 squared minus 2, which is 4. Okay. Minus 2, which is 2. Right? So this is going to be g of 2 plus, what do you know about g prime? 2 times y naught, 2 times 2, which is 4. So this is going to be g prime of 2 outside of y minus 2. What did we say about this approximation? Set it equal to 0. If we can find where this approximation touches the curve, we would get a new value for the approximate root that we're looking for, right? So let's find the y value where this touches 0. What are you noticing about the amount of pen and paper analysis is required to design a numerical algorithm? How much coding am I doing? That's a theme throughout my entire class because that's a theme in solving engineering problems. Code happens when you understand what the hell you're doing. That doesn't happen for me unless I write shit down and think about it deeply. Touches the axis. So what would I do to find the new location? So in other words, in order to find my new approximation, which is going to be g of y naught plus g prime of y naught outside of y1 is the thing that I want to find, I'm going to set the entire thing to 0 and then solve for find this, right? Because that's the thing that I'm looking for, right? Here was my original, this is the one I start with. I go all the way up to the top. I project this thing down. This is the one that I want. This is a new approximation, right? Okay, so this is an algebra problem. I mean, maybe we'll show you how easy this problem is. 5 plus 2 outside of x minus 4 equals 0. How do I solve for x? I mean, I bring the 5 over there. I divide by 2. I add 4. So what would I do there? How would I find my y1, my desired variable value? Yep. So now I've got g prime of y naught outside of my desired thing that I'm looking for is minus g of y naught. This, damn, Natalie, someday when I grow up, I want to be like you. I know, I have to grow up first. All right, I get it. So now you're telling me, yep. I mean, it's really true for all of my students. I want to be like you. I want to walk like you, talk like you, do. Or another way to write this is that my new approximation is the place I started with minus something that looks like this, right? Okay. So once I have this, so this would be my new next guess, right? Okay, so now this is what I call guess number 2. Maybe we call this guess 1. And we would call this one, the one that we started with, we would just call our initial guess, right? Or guess 0. Could you guess what I do now that I have this guess, this approximation? What would I do next? Go up here, take the tangent line. Okay, so let's go ahead and look at this. I'm now going to have something that looks like this, right? So now I can take a new tangent line. What did we say that the structure of the tangent line was? Yeah, it's going to be the initial point plus the derivative of that point outside of y minus the value of that point. But I'm looking for a second guess, right? I'm looking for maybe now or just a few minutes? Whatever. Okay. Didn't want to interrupt. So, if I want my second guess, how would I find my second guess from this? Well, where's the second guess happen? It happens where the tangent line is at 0. So I set the entire thing equal to 0, and I say, what's the input value where the chosen output touches 0? Well, all of these will be known quantities, especially if it's done in a way that I can calculate using IEEE format. Can you calculate the square of a number? What does it mean to square a number? Multiply it by itself twice. There's a multiplication algorithm that we have, right? Derivative, what's the derivative? 2 times the number. You know how to multiply by 2 in IEEE format? Increase the exponent bit by 1. You know how to subtract? So all these things we could do, right? So what's the new value of y2? Just follow along with me. First thing we're going to do is we're going to bring that over there. The next thing we're going to do is to divide. The next thing we're going to do is to add, and we get something like y1 minus g of y1 hat divided by g prime of y1 hat. Okay, well, check this out. Do you see a pattern? Tell me my next guess. Guess. Guess what you are discovering right now? This is Newton's method. This is a very elementary form of Newton's method, but it's Newton's method. For I goes from, assuming that we have set y0, for I goes from 0, 1, 2 until some stopping point. The next iteration will be what? The last iteration minus the value of the function evaluated at the last iteration divided by the derivative of the function evaluated at that, and eventually we'll have some end point, right? Like we'll stop eventually. Okay. So this general algorithm right here is Newton's method, but here's a claim. So this is welcome to Newton's method. Guaranteed you could have generated this if only you were a rich white man in the 17th century that owned land and didn't have to till the fields, right? People say Newton's a genius. I say Newton is a landowner and noble class and was only one of the only privileged people in the world that could spend the amount of time, and he was probably a little socially isolated, right? But let's not take away from his genius. I just think you've heard enough about his genius. Let's talk about his privilege. And the reason I say that is, if you had the same privileges and the same questions arose to you, I guarantee you would have been that person. Okay. So let me ask you this. This G, is it general or specific? So that's the algorithm we're going to try to represent. But what was the specific one? Are we trying to do this for any root, or do we have a specific root in mind? Which root? Square root, the second root, right? Okay, so the claim that we had here was our G, we actually can say more about that G because we knew it was the square root of y squared minus 2. And by the nature of the original problem that we started with, could you guess a really, really nice initial guess? We might say that our initial guess is 2, right? So let me ask you this. What's G prime? Okay. So let's look at this from this standpoint. So our next guess was supposed to be our last guess minus G of our last guess divided by the derivative of our last guess. Okay, let's go ahead and fill that out. So this would be y sub I, not sure what that is yet. What's this? What is G of our last guess? It's our last guess squared minus 2. How about on the bottom? Okay, now I'm going to do something. I've got two fractions with a different denominator. Okay, what's the least common denominator? I mean, maybe we shouldn't write that step down, but this is where, this is one of the reasons that I love take-home exams. My job is not to do math well, my job is to do math right. Speed is an exact opposition to clarity. I would fail most math exams on this campus. And I would do it lovingly, with a smile in my eyes, and I'd give them right back to the professor, and I would say, here you go. Because my job is not to get the right answer quickly. My job is to get the right answer and be sure of it. Right? Okay, so now that I have these, what's the point? I would fail my own, I mean, I'm a teacher that gives a lot of extra time on tests, but if I wasn't, I would fail my own exams. What is all this called? Yeah, I was going to think algebra. Okay, so I could pull the 1/2 out, right? So now I've got y sub I plus 2 over y sub I hat. Did I do something?
Power of 2 up there.
Oh.
So when you cancel, you're going to have...
This thing is 2, you said, right? Thank you, Natalie. Don't give up on an old man. You're supposed to say, someone's supposed to say, you're not that old. Oh, God. Twice? It's funny because it's true. All right, now what? So now I've got 1/2 outside of y sub I plus 2 divided by y sub I. What did we do? Let me ask you this. Where did the initial guess, or the initial, so like, well, yeah, let's finish this problem first. So this is going to be yi plus 1. This problem involves what type of operation? A square root. Have we yet discussed how to implement square roots on a binary computer? No. What operations have we seen? Multiplication, addition, subtraction, and division. So if you had a computer that could do multiplication, addition, subtraction, and division, you wouldn't know how to do this one, right? But what could you do? This one. And if you were able to do, if you've done it once, you could probably do it again, right? So if you just iterated this, what would eventually happen in this algorithm? You'd get closer and closer and closer and closer to the square root, right? Which means we've translated a problem in continuous mathematics into a problem in discrete mathematics, and that problem in discrete mathematics, we have actual physical implementations. Here's the next question for you. Where, oh where, might I get inspiration to do something like this? That's called the square root of 11, right? You don't have to reinvent the wheel. Why was this a 2? Because the thing that I originally tried to solve was a 2. But if the thing that I originally tried to solve was an 11, what would happen? I mean, just propagate that 2 down, right? There's the 2, 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 there's the 2. Where did this 2 come from?
That came from
The derivative, right?
y squared, which is always going to be 2.
Yep. So what if I wanted to take the square root of 11? That would become 11. What if I wanted to take the square root of 7? So we actually have a general square root finder hidden in this thing. Okay. Could you guess what lab 5 is?
This.
Code it. I am going to say I'm going to actually let you teach yourselves on this one, because I learned last quarter I gave a little bit too much structure, and then students didn't. So I told you that student that went over to Berkeley and needed to use MATLAB, and she's like, I wish I would have taught you this. And the moment she said that, I thought to myself, I should lose my job and we should be homeless. Because I failed, right? I failed that student. Because I let that student leave my class thinking that the only way I'm going to know how to use MATLAB is if my teacher has taught me something. So I'm going to see you again next week. I might not, this lab will be due on our finals day, which is not next Wednesday, but the Wednesday after. I don't really want to lecture next on the times that we're going to meet, so we can work on this lab. Be careful. This is a very, very deep rabbit hole. So you're going to write a set of code that's described in this, that you'll have a script file to determine, to set the whole thing up, and then you have a Newton's method root finder that finds the square root of a particular number, right? You're going to have to figure out how the tolerance works. How many digits of accuracy do you have in IEEE numbers? Actually, we can take a break, and I'll start, during the first 15 minutes of lab, I'll start showing you how to think about that problem. And then I'll shut up. So let's do this. It is now 11, is it 11 a.m.? That doesn't sound right. This computer looks wrong to me. It's 11:58. Can we be back at, 11:58. Can we be back at 12:08? I'll spend about 10 minutes getting you thinking about this problem. Then we'll make some decisions about the final exam and about structures and all of this thing. And then I'm going to pack up and get the hell out of here. All right? So let's take a quick break. Or do you want to do it now? Do you want to finish now so that we can get done with the talking portion earlier? Or do you want to take a break and then come back?
Do it now.
Okay, let's not let the loudest person be the, I mean, you're not that you're loud, but like you give me quite fast responses, which
One
you do.
vote.
One vote for now. How many of you would like to do it now? How many of you would like to take a break? Raise your hand if you refuse to raise your hand. Okay. It looks like the folks that said that they'd like to do it now. There were more of you. So I'm going to go ahead and get my MATLAB up and running here. And I might start a new script. This is my sandbox. So we'll call this Lab 5 Sandbox. Okay, so I always like when I'm first doing this just to test the damn thing. So what did we say? We said that y1 was going to be what? The original y value minus, I actually have it right here, right? So what is this? 1/2. I guess I could do it like this, right? Y naught plus 2 divided by y naught divided by 2. And then y2 I mean, one way to do this is like this, right? To turn it into a multiplication problem. So you know what I can do up here, right? Let's call this, well, it shouldn't be exact, MATLAB. So here's a fun question. How do they actually code up the square root function? I definitely don't think it's what we did today. Anybody see a stupid thing that I'm doing right now? Yeah. And there's some people that say, why do you do that? But
For me, that helps match what's
yeah, and it also,
see all the specific things that are being repeated, staying the same incremental time.
so I kind of forget how to make a table in MATLAB. Does anybody remember how to do the titles? I always forget how to do the titles. Well, that's kind of cool, right? Okay, so let's do iteration. Let's call this I value. We'll call this Y sub I. And we'll call this error. And then I might go like 1, 2, 3, 4, 5. Maybe I want to start with 0, right? And then we literally could call this Y0, Y1, Y2. This probably should be a... Do you see somebody teaching himself MATLAB right in front of you? Yeah. I didn't know how to do that before. Okay. So now what I'm going to do... I should really do this vectorized, huh? Yeah, so like maybe I'll call this thing Y1. And then if I call that Y1, I'd probably call that Y2, right?
So we're not starting with 0 anymore.
Yeah, because
Submitted to MATLAB.
we're not fighting the... Yeah, because look what happens when I do 0, right? It doesn't... MATLAB starts at 1, right? I expect you to do this via for loop, but I want to show you sometimes when I'm getting my head around a problem, it's okay to do something called stupid coding. Another way to say that is coding by so now I could put here, I could put 1 up, excuse me, yeah. Well, actually 0 through 5, right? Because these don't, what iteration is 1? Iteration 1 is the 0th value, right? And now this could just be Y. And then check this out. Error is going to be the absolute value of y minus What did I do there? What is an error between my guess and the actual?
Do you want to have semicolons between this to make it gross?
What do you mean?
But
Oh, does it not? You see what MATLAB did there?
yeah.
It's getting mad because it expects in a table. That was a waste of time. Stupid MATLAB. So what's MATLAB telling me about what it expects in a table? It expects it by columns, right? So let me try that again. Column, column, column. There we go. Okay, so guess what I could start doing now? What was your beautiful, amazing, spectacular, incredible question to me? It was like one of the coolest questions I've heard today. When do we stop?
Once the error is below a certain value.
What are they complaining about? There's 9 entries, right?
Trying to work fast to get the answer quickly.
Oh yeah, this one. Thank you. That was a very deep statement.
There.
Okay.
Probably stop after the 5.
Well, check this out. What did I just do? What? What do you see there? What did I do? So first of all, what did I do? I changed it from trying to find the square root of 2 to trying to find the square root of 11. This is an exact 0. Do you know what that 0 means? The number we store in these guesses is identical in terms of IEEE 754 format as what MATLAB calculates for square root of 11. So our algorithm matches identically MATLAB's output for square root of 11 after. What's that? In binary, 52 bits. Yeah, 16 decimal places. That's a good problem. Someday when I write my course to be really good. So what if we did like 1, 7? Oh. Whoa. So this should get you started, right? Could you guess how you might automate this? And then you've got this beautiful question, how do you get tolerance? Here is something that I'm going to build this into the discussion that we have here. I'm specifically not addressing that because I want to make a point as one of the last gifts that I give you. What have I said about MATLAB in terms of the ability to learn syntax? What's the statement that I've tried to make to you the whole quarter about when you want to learn MATLAB syntax, what am I hoping for? Go learn it. Okay. Now, I'm not claiming that between now and next Wednesday you should read everything that you're going to do in Newton's method, because if you try to do that, you won't sleep and you'll fail miserably, because there are tens of thousands of pages written about Newton's method. But I am claiming that there is now an opportunity between now and the next time I've seen you. You've seen an initial code, this is captured on video, etc. There's some work online that shows you a little bit more about how to do this. There's an open question, which is, when does Newton's method break down? Do you see what we're doing here? Did I give you a concrete answer to that? And feel free to use resources. Put a time limit around this. You could spend the entire rest of your career from now until you die, and you will just scratch the surface on the amount of information that you can collect in numerical analysis. All right, so I'll shut up now. If you need to submit your stuff, please do so. I'm going to get my stuff packed up so I can head to my next appointment. I guess the last thing that we wanted to say, it may be the case that the final is a take-home if the coronavirus trend continues to happen in the way that it does. Let's assume for a moment that it's not a take-home. Is it okay that we try our first draft on Monday of next week? Okay, so I'd love please submit to me. If it's the case that classes get canceled, I will have the final ready for you by Monday. My question to you then would be, how should we collect and when should I grade? I really like the idea of being able to grade your first initial draft of the final and get it back to you prior to the end of next week. We might not be face to face again for the rest of the quarter, and I don't want to have this discussion on email because it's going to be ridiculously stupid for me. So here's my question for you. If it's a face-to-face final, it's super easy because we have 4 hours that you can just come in, finish the test, and get it done with, right? If it's a take-home, how do we navigate that? Scan and send, I agree with that statement, but what I mean to say is, when would you like the due date to be? Wednesday? Wednesday at the time that we normally meet? In that case, how would I get them back to you? I'm definitely not going to pay 26 times 50 out of my own pocket, and I don't think that, because I'd have to actually send. That means I'm going to scan every one of your individual. I mean, I guess I could grade them digitally.
Yeah, we could scan and send to you, and then you could grade digitally.
I don't know how to do that. What's that? I don't have any Adobe software on my thing at home. So let's say this. Let's keep an open. No, I don't, sadly. I don't mind putting. The crazy thing is, like, there's an up cost on that, right? And I don't know. What do you think? Do you think I should write my test or learn how to grade digitally first? Probably true for all my classes. So I don't know if I'm going to have the amount of time that I need to learn how to do that in this short amount of time. One option would be that if you send me your things digitally, I could print them off at home, grade them, and then I could put them in a box close to my office by Friday of next week. You could come pick them up on Friday. Test corrections would be due then the following Wednesday. Lab 5 will be due Wednesday of next week. Wednesday of finals week on our last in-class meeting. I had really hoped that we would have at least one more face-to-face meeting that you all would be able to work on this together before the end of the quarter. My prayer was you take the final on Monday, we come in on Wednesday, I don't say a thing on Wednesday, you have 3 hours of working time where you can do what we did last time, which is group work and individual work and all that stuff. I definitely don't want you to get the coronavirus. So why don't we do this? Let's plan to meet, unless we hear otherwise, let's plan for in-class final on Monday, graded by Wednesday, come in on Wednesday. Well, the contingency plan is if we do a take-home, I'll have that for you ready by Monday. I'll send it out via email. You can work on it for 2 days. I'll have much more specific directions on what I expect and how I expect it. You'd submit it by the end of Wednesday, 1 p.m. via email. I would grade it, get it back to you either in digital form if I can figure that out. If not, I would put it outside my office in the box by Friday. You could pick it up. Corrections would be due the next week. Lab 5 would be due Wednesday of the finals week. And we can correspond via email. If it's the case that the coronavirus thing means that we won't do this synchronously, I will be in contact with you all via email about ways that you can get help with that particular lab in a collective space. Does that sound okay? Any questions, concerns, or comments? I am continuing to grade, by the way. Please know that I am grading your work. And I haven't figured that out. This whole virus thing is new to me in my teaching career. It's the first time I've had this. So. My hope is that I can get everything but Lab 5 back to you by the Wednesday of finals week. That may be physically handing it out, or it may be saying, hey, I've graded everything. It's in a binder or a folder outside my office with your number on it. Please come grab it, right? Can I say it? Shut up, Anderson. Yeah? Okay, great.